Alright, so today we are going to study about the strain gauge. As we all know, strain gauge is very important in the applications of mechanical engineering. And strain gauge is usually used in the structures to measure the strain and the stress. So the working principle for the strain gauge is pretty straightforward. When a force is applied to a structure, and we all know that the structure will experience, or the components of the structure will change slightly in terms of the dimensions, and usually we are saying that the structure is being strained. So strain gauge, it will be attached firmly onto the structure, and once the structure is deformed, it can cause the strain gauge, which has been fixed on rigidly onto the structure, it will be stretched. So the wire, once the wire in the strain gauge has been stretched, and it will cause the electrical resistance change of the strain gauge. And from these equations, we know that the resistance of the strain gauge is basically related to the rho, which is the resistivity of the materials. It can be a sensitive functions of the temperature. Then the length, which is the wire length, and the A, which is the cross-sectional area. And considering the changes in R, the resistance of the strain gauge are dependent on the changes of rho, L, and A. So the total uncertainties of the system, the resistance change can be found by finding the changing the having the uncertainties in each of the parameters. And the solution of these uncertainties, in order to get the total uncertainties or changes, it can be the solution is actually given in previous lecture notes. So you may refer to the previous lecture notes in order to determine to refresh your memory what is the solution in order to get these equations. And here we know that the total uncertainties of these three uncertainties can be combined and etched into this equation, where delta rho divided by rho plus delta L divided by L minus delta A divided by A. Right, and we also know that the area, the wire is basically having a diameter. So the cross-sectional area of the wires can be determined by pi d squared divided by 4. Right, so therefore in this case, the changes in area is basically related to 2 to the delta d divided by d. And knowing that the axial strength is given by delta L divided by L, and delta D and D is the transverse strength, and by using the Poisson ratio, we can substitute the changing the getting the delta L relate delta L and delta D by and D, which is obtained from the delta A from the area. So we can basically relate it to the with the Poisson ratio. So we know that transverse strength is actually equals to minus nu and then epsilon A, the axial strength. So eventually the total changes delta R divided by R, these equations can be further simplified into this form, right, which is dependent on the materials and then also the strength. Right, so assuming that the resistivity of the material in the same temperature remains constant, therefore we can see that the changes in the resistivity of the strain gauge will be linearly dependent on the epsilon A, the strain gauge. Another very important equations for that define the characteristics of a strain gauge is actually the the gauge factor. So gauge factors is actually equals to the delta R divided by R and divided by the strength. Okay, just a very piece of advice. When you are using a strain gauge, make sure that the strain gauge is oriented in such a manner that it is facing towards the sensitive direction. So if you want to measure the strain coming in this direction, then you should orient your strain gauge in this manner. Whereas the side way of the strain gauge will be so-called as a insensitive. So that any forces or the strain coming in these directions, it will not cause any changes to the resistance change. So a very simple examples on the strain gauge. A strain gauge is, let's say, having a resistance of R equals to 120 ohm initially on strain, and then the gauge factor of the strain gauge is actually equals to 2, and the gauge is applied to a materials with a Young modulus equals to 200 megapascal, and then the maximum stress of experienced by the structure is actually equals to 50 Pascal. So you are asked to find what is the maximum resistance change of the gauge. So in these examples, we first of all we need to determine what should be the strength, as the strain gauge is actually measuring for the strength, not the stress. Therefore, we through the Young modulus equations, we will be able to relate the stress with the strength. So we know that the strength is actually equals to sigma divided by the Young modulus. And we know that the maximum stress is 50 Pascal. And then the Young modulus is 200 megapascal. So the strength is 2.5 times 10 to the negative 4. Alright, so from the gauge factor equations, gauge factor we know that is equals to 2. And delta R is the parameter that we want to determine. Unstrained resistance is the 120 ohm, and epsilon is 2.5 times 10 to the negative 4. Therefore, we can find that the delta R, the resistance change after being stressed, will be 0.06 ohm. Strain gauge is usually used together with a signal conditioner, and two critical effects are normally considered in the design of the strain gauge signal conditioner. First of all, small resistance change of the strain gauge has to be carefully amplified and transformed from the resistance change into a voltage change. So, second effect is the temperature effect experienced by the strain gauge has to be compensated. Therefore, the signal conditioner should be able to eliminate the temperature that has been masked onto the strain changes. So in this case, Wheatstone bridge is normally used to measure for the resistance change. Wheatstone bridge can be used in different form. One common form that has normally been used is the one-arm bridge. In such kind of arrangement, one strain gauge is oriented in the sensitive direction in such a way that this gauge is called as an active gauge. And the main use of this strain gauge is to measure the strain experience when the force is applied in the sensitive direction. Another strain gauge will be aligned in the insensitive direction, and this strain gauge is what we normally call as a dummy gauge. And this gauge will not respond to the force that has been or the strain that has been applied in the directions. The main use of this dummy gauge is just as a detector of the temperature change. So since these two strain gauges are having the same resistivity, therefore temperature effects onto the two strain gauge are assumed to be equal. Therefore, any changes onto this dummy gauge can be effectively compensated through the Wheatstone bridge. Dummy gauge is usually placed at the third resistors, whereas the active gauge is at the placed onto the fourth resistors in the Wheatstone bridge. Another more useful form of a Wheatstone bridge is what we so called a half and full bridge. We usually we use either only two gauges, and if you are using only two gauges, then this is half bridge, or all four gauges, then that is the full bridge. In the strain measurement, a full bridge that has been shown in the figures below, it provides maximum sensitivity to the loading. And this at the same time will compensate for the temperature effects. As you can see in these pictures, in these figures, the four strain gauge are arranged in such a manner that the R1 and R4 is located on top of the structures, and R2, R3 is placed at the bottom of the structures. So this is the top view and this is the side view. Alright, and R1 as the first sensor, R4 as the fourth sensors, and you can see that as the force is being applied onto this beam. Therefore, the top side of this beam will experience tension, whereas the bottom of the bottom side of this beam will experience compression. Therefore, you can see that the resistors at the top will has experience a positive resistance change, and also same thing goes to the fourth strain gauge. And for the strain gauge 2 and strain gauge 3, since they are experiencing the compression, so they are having negative delta R, and R2 also negative delta R. If this strain gauge or this structure is applied to the axial force instead of a moment, then this resistance change will be all equivalent. That is, all of them will experience delta R, positive delta R, if it is tension. If compression, if at these two sides, and then all of them will experience negative delta R. Alright, let's consider this example. Let's say we have a strain gauge R2 and R3 actually experience the tension, and strain gauge R1 and R4 they are experience compressions under this loading of the force F. So show that the delta V, okay, which is the offset voltage of the Wheatstone bridge over the supply voltage, is actually equals to delta R divided by R. This is a full bridge, and in this case, note that the resistance change of each compressed strain gauge, that is strain gauge 1 and strain gauge 4, that experience compression, they should be negative. Whereas the resistance of tension strain gauge, which is R2 and R3, they are experience positive delta R. And initial unstrained resistance is actually equivalent. That is R1 equals to R2 equals to R3 equals to R4 and R. So we know that the Wheatstone bridge equation is basically given by this equation. Substitute R3 and R2 are experiencing tension, so they are having positive delta R and positive delta R. Whereas R1 and R4, they are experiencing compression, so they are having a negative delta R. And substitute into all these terms, and then we also know that R1 equals R2 equals R3, R4, and it is equals to R. So substitute all this into the equations, and finally we can simplify and we get these equations proven. Examples that we have seen so far are related to the measurement of strength, but in real life we are more interested in the measurement of force. Therefore, a load cell is required. Load cell is a transducer that measures the deformation produced by force or wave. And this transducer is made out from a very simple structure, and with the strain gauge attached firmly onto the structure. Load cell are usually just elastic members, and there are two types of load cell that are commonly used. One type is the axial force load cell, which is used together with a link, and another kind of a load cell is the bending moment load cell, using together with a beam. Right, for the axial force load cell, uh, this axial force will be applied onto an elastic body, and these elastic body are usually having a well-known geometry. And for example, a box, a rectangle, with a depth of A and then the width of B. By applying the force axially onto this very simple load cell, we can easily relate the force with the strain experienced by the gauge. So let's say the stress is given as sigma equals to F divided by AB, and then the strain is defined as the ratio of changes of length over the initial length. And also we know the Hooke's law, sigma is equal to E epsilon, and the gauge factor is given as this equation. Combining all the equations above, equating the sigma or the stress, Then we can get the equations which is in this form, and we can know that the R resistance is constant, gauge factor is constant, the Young modulus A and B are all constants. Therefore, we can simply derive that delta R is actually the change of resistance is proportional related to the force. All right, let's look at the examples. Let's say an axial load is applied to a link connector, and the change in strength is measured by applying 4 strain gauges as shown below. So this is a pictures, the schematic drawing, and we can see that one strain, the strain gauge is applied in the sensitive directions, and another strain gauge is applied in the insensitive direction. Then R3 and R4. R3 is insensitive, R4 is sensitive. And these are all 4 gauges applying to measure for the force. And then 2 strain gauges, which is R1 and R4, are used for the strain measurement, whereas the other 2, which is R2 and R3, they are used as a dummy gauge for the temperature compensations. Let's say the maximum force applied is 400 Newton and the gauge factor GF is equal to 2.2 and the modulus Young is 69 gigapascal and then the current flow is 25 milliamp. So you are asked to determine the maximum output voltage of this load cell. Let's say the initial resistance of the gauge is actually 120 ohm. So the whole signal conditioning circuit, which is the Wheatstone bridge, is having this arrangement. R1, R2, R3, and R4 is arranged in this manner. And we have a very simple structures where with the width of 1 centimeter and the thickness of 1 mm. Alright, we know only the current. In the question, it said that the current flow to the each of the sensor strain gauge is actually 25 milliamp. Therefore, we need to know what is the voltage. Okay, the voltage supply onto the Wheatstone bridge, and this can be determined by using the Ohm's law. We know that a Wheatstone bridge is basically just a pair of voltage divider consisting of a pair voltage divider R1, R3 and another voltage divider R2 and R4. So we just, and since this is in parallel orientation, so both voltage divider will be having the same voltage. So just tap the side of R1 and R3. The voltage will flow through R1 and R3 and back to the bottom. So voltage V is equal to I multiplied by the R1 plus R3 as these 2 resistors are connected in series. So current we know that is 25 milliamp and R1, R3 are all having the same resistance 120. And this will tell us that the voltage applied to the Wheatstone bridge is actually 6 volt. And from the Wheatstone bridge, we know that the Wheatstone bridge equation, delta V, the offset voltage related to the voltage supply is actually given by this equation. And from the figures, we learn that R1 and R4, which is in the sensitive direction, will be tension. R2 and R3, which is in the insensitive directions, they are just dummy and there won't be any tension experienced to R2 and R3. Therefore, we can just substitute R2 and R3. There is no deformations in which is just a dummy. And R1, R4 in the sensitive direction. So there is deformation. So this tension, we have a positive delta R. And same thing goes to here. R1 sensitive direction, we have a delta R. R3 as a dummy, there is no resistance change. R2 again a dummy, there is no resistance change. And R4 there is a resistance change. And by simplifying the whole equations, Wheatstone bridge equations, and we will find that delta V divided by Vs will give us negative delta R divided by R then divide by 2 plus 2 multiplied by the delta R divided by R. And maximum strength, on the other hand, can be determined from the Young's modulus equations. And we know that sigma, the stress, maximum stress, is given by the F maximum divided by the cross-sectional area. So we know that the maximum force is actually given as a 400 Newton. And the cross-sectional area, we have a 1 mm width and then 1 centimeter width and a 1 mm thickness. So this is to give us a cross-sectional area. Young modulus is 69 gigapascal. So the maximum strength experienced by the structure will be 5.8 times 10 to the power of -4. And once we know the strength and through the gauge factor equations, we will be able to tell what is the ratio between the resistance change with relative to the initial resistance. And delta R divided by R will be equals to the strength multiplied by the gauge factor. Alright. So once we know delta R divided by R, we can substitute this ratio into the previous equation derived from the Wheatstone-Bridge equations. So we know delta R divided by R is equals to 5.8 times 10 to the power of -4 multiplied by 2.2. So delta R divided by R equals to this, and then 2 plus 2 again multiplied by the delta R divided by R. We substitute delta R divided by R, and we can calculate for the offset voltage. And we know that knowing that the voltage supply is 6 volt, therefore it is expected that the offset voltage will be -3.82 millivolt. So also take note that positive or negative of the delta voltage is actually not so important, since it is very dependent on how you place the strain gauge. So if let's say we are placing R2 and R3, right, instead of placing R1 and R4 in these directions, let's say we are instead having the R2 and R3 as a sensitive direction and R1, R4 as a dummy. So in this case, we will get a positive offset voltage. Alright, so basically that is for the axial force load cell. Alright, let's look at another kind of a load cell, which is the bending moment load cell. So as we have learned previously, bending moment load cell is used together with a beam. So usually this bending moment load cell will have a configuration that looks something like this. In this case, the strain gauge will be used to measure for the bending load, where the load is applied in this direction. Okay, we can relate this moment of force F to the position of the strain gauge through this equation, where the moment is equal to force multiplied by the distance of the strain gauge away from the F. And then according to the Coulomb's law, the moment divided by the inertia, or the I, which is the second moment of area, is actually equals to the stress divided by the h, and h is the distance from the neutral axis. And this beam have a geometry of a rectangle shape with a width of A and then thickness of B. So combining the equations above, two of the equations above for the moment and also the Coulomb's law, we will be able to derive that the stress is actually equal to Fx divided by h divided by I. And given that the second moment of area of this rectangular beam is actually AB cubed divided by 12, and also the h, which is distance from the neutral axis, is just the thickness divided by 2, B divided by 2. So substitute all this information into the equations here. So we get the stress is actually equal to 6x divided by AB squared multiplied by F. We also know that from the Young's modulus, the stress is equal to E epsilon, and gauge factor is delta R divided by R over the epsilon. Therefore, the stress is E over epsilon multiplied by the delta R divided by R. And substitute this into the equations above, and you were equating for the stress, and we can see that delta R divided by R will be equal to the 6 GFS divided by the EAP squared multiplied by F. And since the gauge factor is a constant and the distance of the gauge from the force is also constant, Young modulus A and B are all constant. Therefore, we can say that by using this bending moment load cell, delta R over R will be proportionally related to the bending force. Alright, so now let's look at the examples here. Given the resistance values of all strain gauge are initially R1 equals to R2 and R3 equals to R4, and they are all equals to 120 ohm. And then the voltage supply to the Wheatstone bridge are equals to 9 volt. And you are asked to calculate for the force that is applied over here if the offset voltage recorded at the bridge is actually 20 millivolt. And we know that the beam are having a structure, the width is equals to 10 mm, and then the thickness is 1 mm. And the Young modulus is equals to 206 gigapascal, and the distance of the gauge from the force is equals to 50 mm, and the gauge factor is known to be 2.4, and the circuit for the Wheatstone bridge is given as this. Right, so in this case, you can see that R2 and R3, they are all experience the tension, whereas R1 and R4, they are experience compression. So in this case, substituting this resistance and also the tensions and compressions into the Wheatstone bridge equations. So R2, R3 experience tension, we have a positive delta R, and R1 and R4 experience compression, we have a negative delta R. And through the derivations here, we know that delta V over Vs is now will be equal to delta R divided by R. And since in the question it says that the offset voltage delta V is equal to 20 millivolt, and we also know that the voltage supply is 9 volt. All right, so we have delta V over to Vs is actually 20 millivolt divided by 9 volt, and we don't know what is the delta R. Initial resistance is 120 ohm, therefore delta R is given as 0.26 ohm. Right, so once we know the delta R, and from the previous bending moment model, which is derived previously over here, delta R is related to the force by these equations. So using these equations, right, we know delta R, we know the initial resistance value, gauge factor also know it, and then the length of the strain gauge from the force is also known. EAB square all are known, so we can just plug it in to calculate for the force, and it is determined to be equal to 6.36 Newton. So basically this concludes everything about the strain gauge.